So here are the notes for day 49. It's a continuation of inverse trig differentiation. Last time we derived these three formulas. 1, 2, 3. This time we'll derive one more, and then I think you can figure out the pattern for the final two. But if you look at the bottom, all of these formulas that you need to get memorized are on page 378 of your book. So we'll be talking a little bit more about these six in a few minutes. But let's go ahead and try and derive the secant, the derivative of inverse secant. So just like last time, we're going to take and redefine, and we're going to say this inverse secant of x is equal to y. So y equals inverse secant of x, which means secant of y is x over 1. I can turn that into cosine of y equals 1 over x, and now draw my triangle. So I'm going to have an angle of y, and if cosine is 1 over x, that means adjacent over hypotenuse gets labeled that way, which means this other side, the opposite side, is hypotenuse minus adjacent side squared, which is x squared minus 1. So now when I go to take the derivative of cosine y, I'm going to get negative sine y times y prime equals the derivative of 1 over x is negative x to the negative 2. Solving for y prime equals negative 1 over x squared times negative 1 over the sine of y. So putting that all together, we get y prime equals a positive 1 over x squared, and then the reciprocal of sine, using your diagram, sine is opposite over hypotenuse, so that would be the square root of x squared minus 1 over x. So the reciprocal is x over the square root of x squared minus 1. Simplifying a little bit, we get y prime is 1 over x times the square root of x squared minus 1. And that matches what we have down here for the derivative of inverse secant, the derivative of arcsecant. Now they did things in terms of u. In case you don't just have an x there, but maybe something that's a function of x, they have u prime, which is just the chain rule, the absolute value of u, and then the square root of u squared minus 1. Where did the absolute value come from? Well, that's really quite difficult to explain. There's a box at the top of page 376, a big red note that says there is no common agreement on the definition of arcsecant x or arcsecant x for negative values of x. And if you'd like to understand why this is an absolute value sign right here, you're more than welcome to read the box on page 376. But from this point on, I would say just memorize that when you take the derivative of arcsecant, there's going to be absolute value bars around that x quantity right there. Okay, so the other two follow a similar thought process. You set up your triangle and do your derivatives that way. The six that you need to get memorized are down here, formulas 19 through 24. Hopefully you already have 13 through 18 memorized, but one thing I want to point out, very soon we're going to be taking antiderivatives of these things, and I want you to make some connections between a couple of these. If you look at sine and cosine, those are going to produce identical results with the exception of a negative sign. If you look at tangent and arctangent, those are going to produce the same results with the exception of a negative sign. And if you look at secant and cosecant, the derivatives of their inverse functions are the same with the exception of a negative sign. So when we go to take antiderivatives and when we go in the backwards process, I look at something and take the antiderivative to produce an inverse trig function. We only need to memorize 3 because there's the difference between the blue circles, the red circles, and the green circles is just a negative sign. You'll see what I mean when we start day 50. Okay, first example, this is an application problem, and I apologize for the gigantic, scary-looking animals, but one hallway which is 4 feet wide meets another hallway which is 8 feet wide in a right angle. What is the length of the longest ladder which can be carried horizontally around the corner? So this is kind of hard to visualize, and your slide has some sort of animation text on it, but if I click play on this movie, you'll see that as the ladder travels and tries to get around the corner, the length that will fit around the corner keeps shrinking. And if we can find that smallest length, that will be the longest ladder that can fit around the corner. It's kind of like when you move into your dorm in college, trying to get a couch up and down the stairs, you've got to navigate some really tight corners. Same kind of an idea. You want to know what length is the longest length that can fit around the corner. So we want to find the shortest possible distance for that ladder there. Okay? So I've added some labels onto our hallway. This hallway is 4 feet wide, this hallway is 8 feet wide. The ladder creates two triangles, both of which they're similar triangles. So they both have an angle theta there. And the statement that we're gonna create is the length of the ladder, which is A plus B, winds up being 4 over sine theta plus 8 over cosine theta. Where did that come from? A is sine of theta, opposite over hypotenuse. B is cosine of theta, adjacent over hypotenuse. So 4 over sine theta plus 8 over cosine theta is A and B respectively. That turns out to be 4 cosecant theta plus 8 secant theta. We want to find the rate of change of the length with respect to the angle. So taking the derivative, dl d theta is negative 4 cosecant cotangent plus 8 secant tangent. Critical numbers, take the derivative, set it equal to 0. I turn cosecant and cotangent into their sines and cosines. I turn secant and tangent into their sines and cosines. Let's bring the negative side over. You wind up with this, doing some cross multiplying. Cosine cubed is 2 sine cubed. Bringing the cosine cubed over, you have tangent cubed is 1/2. Tangent of theta is the cube root of 1/2. Theta is the inverse tangent of the cube root of 1/2, which is roughly 0.671. To prove that that angle produces a minimum, you would have to set up your number line. You need a calculator to evaluate this, obviously. So I put 0.671, and then I realized that the angles that the ladders are going to make, that the ladder will make, is anything between 0 and 90 degrees, or between 0 and pi over 2 radians. Everything we do in our calculator and calculus is in radians, so make sure that your calculator is in radians for all these calculations. Anyway, I picked an angle below 0.671, which is pi over 6, which is 30 degrees. An angle bigger than 0.671, so I picked 60 degrees or pi over 3. I plugged those into the length function. So I plugged in pi over 6 for sine, pi over 6 for cosine, using my calculator, and found out that that was negative and this is positive. Therefore, the length is decreasing than increasing. So the minimum length is 0.671. So as I go around this corner, the angle that produces the minimum length is 0.671. When I plug that into the length function, I will get plug it in here when theta is 0.671, 16.648 feet. So a ladder that's 16 feet will fit around the corner, but a ladder that is 17 feet will not. So this last example will be a little bit more reasonable. Television camera ground level is filming the liftoff of a space shuttle at a point 800 meters from the launch pad. Let theta be the angle of elevation of the shuttle, and let s be the distance between the camera and the shuttle. So from the camera to the shuttle is s. The angle of elevation from the ground up to the shuttle is theta, and the camera is 800 meters. So I got this obviously out of a book, but it's a really dark copy, so I redrew it here. Camera is here, looking at the space shuttle up there. That distance is s. The angle of elevation between the ground and the shuttle is theta, and the camera is 800 meters from the initial launch site. So write theta as a function of s for the period of time when the shuttle is moving vertically. Differentiate the result to find d theta dt in terms of s and ds dt. So two things to do. Write theta as a function of s. Well, I have a right triangle here, so theta as a function of s isn't too bad. We have cosine, which is adjacent over hypotenuse, is 800 over s. So if I solve that for theta, we get theta is the inverse cosine of 800 over s. Okay, taking the derivative, if I want d theta dt, but I've got theta in terms of s, I need to find d theta ds and then multiply that by ds dt. Luckily, we were told that we can write our answer in terms of ds dt. So this part here is going to be part of our answer. So taking the derivative, what happens is the derivative of the inverse cosine is this quantity right here. By the chain rule, I need to take the derivative of this, so then I wind up with another negative 800 over s squared. And then because of the change in variables, I need times ds dt. And again, this can stay in our answer. So last step, we're going to do a little bit of simplifying and rearranging. Negative 800 times negative 1 is obviously positive 800. I'm going to put the s squared out front, but then I'm going to take an s squared out of this square root thing here. So if I were to take a 1 over s squared from the inside of the square rooting, that becomes 1 over s, and what's left behind is an s squared, and then no denominator in this fraction here. To verify where this 1 over s came from, square this and bring it back inside. 1 over s squared times s squared is 1. 1 over s squared times 800 squared is 800s quantity squared. So that's how do I get rid of the denominator, by bringing it out. S squared times 1 over s simplifies into this, and our final answer is that. And we're allowed to have s and ds dt in our answer because we were told that that's acceptable.